म्यू माइनस एक्स का होल स्क्वायर बाय एन का सम. तो मतलब 55 माइनस 50 विच इज इक्वल्स टू 5, 60 माइनस 5 का स्क्वायर प्लस 0 स्क्वायर. सो 25 स्क्वायर प्लस 25 नो सॉरी 5 स्क्वायर प्लस 5 स्क्वायर प्लस 0 डिवाइड बाई 3 विच इज इक्वल टू 50 डिवाइड बाई 3 विच इज इक्वल टू 16.667. तो जैसे मैंने पिछली वाले लिया था कि स्टैंडर्ड डेविएशन 10 ले लिया था. नाउ in this case our mean will still be 60 because our answer is around 60. In this distribution 60 plus 16.667 which is 76.667 and 43.33 इनके बीच में म्यूटेट करने की प्रोबेबिलिटी ज़्यादा होगी. सो नाउ सिंस आवर एग्जाम्पल वाज 50, 60, 55, when we come to 50 and it crosses the PM, which is the probability of mutation barrier, if it does not cross, then we will simply not mutate it. But if it does cross and it is going to get mutated, then the probability of it getting mutated between 43.33 and 76.66 is 2/3 times more, is almost twice more than the probability of it getting mutated below 43 or more than 76. Because since this area is 2/3, so that means rest of the area is 1/3. Hence the probability of it getting mutated is twice than mutating outside of this range. I hope you samajh aaya. And every time we mutate, these values are going to change. These values might change to 52, 60 and 56. Right, then this will have a different standard deviation around 60. When this has a different standard deviation, it will have a different range within which it will mutate with a higher probability. And when it will have a different range, it will adapt itself, basically. That's what it means. Instead of us providing us with the standard deviation value, the standard deviation value is calculated on the data, on the gene we have. Now, like I said, this becomes part of the chromosome representation. 50, 60, 55 and 16.667 on this is the gene and this is part of the gene as an extra dimension added to it. This is going to keep mutating and this will also mutate dependent on this. As these values change, the standard deviation of the values will also change. I hope this is understandable. Like when you read the notes, I think most of it will become clear as you go. Now when we talk about adaptation, it could be possible that we are self-adapting into the wrong direction, right? For example, around 60 all the values start converging towards 50, 50, 50. Well, we don't really want that, right? We want the values to converge towards 60, 60, 60. So we have to perform some sort of evaluation, and since this is self-adapted, there is no way we can control it externally, right? We can't be like, okay, now that 6 iterations have already taken place, let's change the standard deviation from 10 to 20 and let's see where the direction goes. Instead of doing this, self-adaptive methods should improve themselves. Now to improve themselves, there need to be a criteria on which they improve, right? So either every time we make offsprings, so now that we've mutated 50, 60, 55 either to 52, 60, 56, or we have mutated it to 48. Since the value was 43, it can very well take 48 and 52 with the same probability. It could be possible that it mutated in the wrong direction. So it became 48, 60, and since this 55 can become even larger, 72. Well, we don't want this. We want the values to come closer to 60 rather than go away. So we can evaluate the fitness on this. And when we evaluate the fitness, we will get a very low value. That means this solution is not very good. Hence, this, this step size, this standard deviation is not a good standard deviation, and we should go back and change it. This is called direct evaluation as we calculate on the fitness. Now, indirect evaluation is when we don't calculate on the fitness. Rather, we compare offspring and parent fitness. So, if our fitness of 50, 60 and 55 was, let's just say, 100, and we created its offspring and one of its fitness was 88 and the other was 95, then we will obviously choose the fitness with 95. But if we get an offspring of 108 fitness, then we will choose 108 over 100. So instead of comparing directly the fitness value, we evaluate and compare it with the parent. I think this can be, you can just read this example and it's it's more intuitively explained. You write, we compare the fitness of offspring to the fitness of the parent individuals. If an offspring has better fitness than its parent, such as that the step size used is more favorable. Like these different offsprings will be calculated with different step size, with different standard deviations. So we can either choose standard deviation A, which produces 88 fitness, or 95 fitness. We will obviously choose the standard deviation with producing higher fitness, 95 fitness. Now let's come to, now mutation, right? Now that we have talked about there are n dimensions in our candidate solution. In the case of the equilateral triangle examples, we have been exploring 50, 60, 55. There are 3 dimensions, right? Side A, side B, and side C. Now, for each side and for each dimension, we will have 2 parameters. One being the standard deviation and other being tau, which is basically the learning rate. The learning rate is for the standard deviation, which determines with what rate the standard deviation changes. And standard deviation changes the mutation, right? So learning rate changes the rate of mutation. Like in a way you could think about it like that. For uncorrelated mutation with one step size, 50, 60 and 55, all 3 of them will have the same learning rate and the same standard deviation. So you could say that for A, XA will be equal to original X, like X, the next offspring for side A, X plus tau into some random value that we will choose with mean 0 or mean actually 60 and standard deviation tau. For XB also we will choose XB offspring. We will choose the previous value of XB plus tau into, this is not X, this is into a random value chosen around mean 60 and standard deviation this. Like for all of these, tau and this remains same. Standard deviation and tau, both of them remain same for XC also. Right, this is what we have explored till now. And this is what is called as uncorrelated mutation with one step size. Now, uncorrelated mutation with n step sizes basically means for each of these dimensions, we will have a different standard deviation and different learning rate. Different standard this will have and for correlated mutation basically mean, so I'll just write the formula for this as well, will be equal to XA, like the original value, plus alpha X into this, plus tau A, alpha A plus. For B, it will be XB plus tau B. Like I'm not actually multiplying the standard deviation. I'm saying we choose a random value of the distribution around the mean with standard deviation. This is what I mean. I feel like I've repeated the sentence quite a bit now. Mean and different. So now this means that each of these dimensions will mutate at a different rate and with a different standard deviation, with values chosen with a different standard deviation. Now for correlated mutation, I would like to take up an example and explain how I understood these 3 things. Imagine you have to design a robot. Now for that robot, you will have a lot of things like arm size, leg size, torso size, and all of that. For example, if you want to increase the size of the robot, we can increase its arm length, leg length, and torso length at the same rate, right? the robot of this side will just become twice as this size, where its torso will become twice, its legs will become twice, its arms will become twice. This is a form of uncorrelated mutation, since we are increasing all these 3 dimensions at the same rate with the same type. So all of them become twice. Now if we want to optimize its arm will have both 2 parts. This is the elbow, so the upper arm and the lower arm. Now you can't say that if you want to optimize the arm to work in such a way that you should increase both. So the rate at which the lower arm length increases is same as the rate the upper arm length increases. We might want to increase the upper arm length at a different rate. For example, we should only want to increase it by 0.6 times, and we want to increase the lower arm rate by 0.4 times, right? So this is where both of these are dimensions of the same problem of optimizing the robot's arm, but they are growing at a different standard deviation and a different learning rate. Now think about correlated mutation. Think about now if you want to check the weight of the robot, right? As we increase the arm, leg, torso weight will depend upon all of these 3 values. So as arm increases, weight will be equal to the increase in arm plus increase in leg plus increase in torso. So correlated is something where each of the values increase dependent on each other. If we create a new mutated value of x, it becomes xa plus standard deviation around xb plus c. So see, the new value is dependent upon all 3 variables, on how all 3 of those genetic dimensions are evolving. I hope this example made everything a little more easier. Like if you have a look at these equations and you just write them down, I think you will get a very good understanding. Just reading them will also, I've written a lot of too complex is because it literally is too complex. I'm not going to bang my head against the wall and try to understand the equations written in the book. Even if the answer comes for like 5 marks, I'll just skip it. Now we come for recombination operators. Now that we have already covered mutation, for every representation in the unit 2, we have done both 2 parts, mutation and recombination. Let me just have a look at the subtopics again. And okay, I have erased that. But